Okay, so just watch it, and then so that you understand what is that we. So with this, once you have this one, no, can you see the video running right now?
Yes, sir.
Yeah. Okay. You see this one. See, this is okay, and then yeah, you see this one. This is simple, no? You see here, R cap is this one. R cap is this. So you just calculate your R cap. What is your dou R by dou theta is actually minus it. That is nothing but your theta cap. So the derivatives of these unit vectors are basically other unit vectors. It matters. Okay. Dou theta cap by dou theta also will become minus R cap. Okay. Dou theta cap by dou R may be 0. Okay. Like you see here. So because physically you can see it is not varying. Right. You understand? See, even if you change theta, even if you change, for example, theta cap, even if you change R, okay, you move along R, theta is same, no, this direction is same. So that shows that physically this is 0, right? So dr cap by dr is also 0, because even if you change, no, along with R, same direction, finally your R cap is not changing. Physically, these two, first, whatever you are seeing here, no, which I'm my pointer, whatever is I'm rounding, those are all physically you can see. And the remaining two, just now we have seen, no, sometime back. I think, where is that? Yeah, from here you can easily see it. So just take cos theta sin theta, you calculate with respect to theta, you will see that. That's enough. So using this, you do that U cap, these things, okay? Exactly, I'll show you what is that I want to tell you. Okay, here. So this one, this if you calculate all these things, you will get it properly. This is exactly what you get. Okay, but we are avoiding that throughout the course, so we have avoided. But in order not to avoid, tomorrow if you need, so that is the thing. That video, whatever I already shared you. Okay, so go through that video. Okay, and then you can actually derive this one. So try to derive this, try to write with your curvilinear coordinates, you will get this extra terms. So this extra terms, whatever I'm highlighting here, it's coming from the derivatives of the unit vectors. Okay. So if you actually it's a little bit work you have to do, so that's what is it. So we are completely avoiding this and trying to use the textbook. What it says, the textbook says is that I'll open whatever I shared, So for example, here, yeah, you look at this one. That is that one that we have done. Yeah, here you see this. It says that the form of LHS chosen here is preferred to that of the last example because of the form Q means here U dot grad U is difficult to evaluate directly as the unit vectors is not constant. So it is actually depending because you are in R theta, no? So it changes. If you change the theta, maybe R may be changing with respect to theta. So that's what is the meaning, right? You change the direction of theta, R radial direction is changing, no? So it depends. So that's why they are not fixed. That's what is not constant means that the unit vectors are not constant is that in the cylindrical coordinate system, R and theta. Okay. So that R cap, theta cap are actually it's changing. So once you change the position, they're also moving. They're not fixed things. But what happened earlier? The one that you have done, no? So in this case, why it didn't matter? Because here also they use thinking that it is R and theta, but we have done without R and theta, right? Without this thing, without this term, right? We simply worked with this U dot grad U only yesterday. We didn't have any issue. We got the same answer. The reason is this R and theta only dependent. So R and Z anywhere independent. So they don't depend. So if you move along in the RZ plane, so they are actually fixed. You understand? Rishabh?
Yes, sir. Yes, sir.
So just go through. So next class, what I do is I'll try. So for that reason, we are replacing that in the Navier-Stokes equation, that second term now, we are replaced with this one, whatever you are seeing in the equation 330 on page. So through this, I think we are going to work. So this is easy to work out. We know the formula that we derive. Del cross U, that we know how to derive. This is the formula we already gave. And this cross product. The cross product is simply you try to see what is the usual cross product. Okay. It takes simply finally cross product of something is like, R theta. Okay. Theta cap cross R cap is actually will go to Z cap. So with that, whatever the usual way you can make unit vectors cross product. Okay. So that if you do, you calculate finally this, and then that you are going to put it and finally get your equation. So the flow in the that's what we will do tomorrow. And whatever you are seeing here, the 8.11 cubes of uniform cross section. So far, you are dealing only with the circular kind of cylinders, right? Circular tubes, circular cylinders. If you don't consider as circular, some kind of arbitrary, okay, some kind of triangle or whatever, those kind of tubes, if you consider, then you can't use your cylindrical coordinate system. So for that reason, you may deal with this Laplace equation in those two variables, x and y variables. So this forcing function will come like that. Okay, so you will have some separation like earlier, but right now here you cannot solve this. This is a Laplace equation. So Laplace equation has some uniqueness theorem, so that I will show you. Okay, so maybe next class or 1 more hour. So with that I will close it. You understand? So that's what
Yes,
uniqueness theorem. So I will show the uniqueness theorem not from this. I will show you very nicely in general Robin kind of problems. Laplace equation, like a mathematical way, there is a uniqueness. Okay, once you know that this problem has a unique solution, so how they deal with this way. So finally, you pick up some problem. You see this tube having uniform elliptic cross section. If you take it, so this is the this is the thing. You're just looking for one solution. Okay, I try to it just by inspection you see that this actually satisfies this equation. With some constant k, they put it and try to put it here. You calculate that k, so that solves your W. I know that it is unique solution, so this should be the unique solution. That's how it goes here. Okay, you understand? How am I solving this? Solving this, whatever I'm showing, this Laplace equation equal to some right hand side. I am trying to look for. This is some kind of tricky way. Okay, I know that this has a unique solution. This equation. Okay, so if I just by trial some solution, if I look for, so that involves this boundary, whatever the domain you involve, 1 minus of that into some constant you put it. Try to now substitute. Assume that you just by answers you assume that this is your solution W. So you substitute into this so that you can find your k. So k, once you understand, once you derive that k, uniquely determine that k, come back and put here k. So that will that is actually our solution, one solution. But you know that this is a unique solution, right? This is the unique solution, that uniqueness theorem I give you. So that's how this is the solution. So once you have this W solution and P, okay, coming from this, where is that one? So here, for example, here, yeah, you have this one. Similar way, whatever the way we are doing now, we are trying to solve this pressure and this unknown W. W is basically or flow in the W direction, Z direction, Z component of your velocity W. Okay, but that depends on both X and Y. So far, what you have seen is only depending on only one variable. So this is the ODE. So we are able to solve directly. So here, this is the PDE. It becomes a PDE. So you need a uniqueness theorem, and then you know how to solve it. Some simple way is just by this is the trick. Okay, just look for some answers. Otherwise, also we can actually solve by separation of variables depending on the domain. No, so this is the elliptic domain. So elliptic domains, this is the trick you can just follow. Okay, so this you understand. Otherwise, if it is elliptic domain, how do we solve it? You convert this into circular domains and then use your polar equation. Okay, R and theta variables, you solve it. You can easily solve it mathematically. It is a roundabout, but these are the people who have done in fluid mechanics. These are the equations that come in the fluid dynamics, and they use it and they use this trick, like You know the uniqueness, solution is unique. And I need only one solution. I am looking for this way. You put it, it solves. You understand? The advantage of this is on the boundary, the W is 0. Okay, that is what is your no slip condition. Boundary condition is also satisfied, right? Once X and Y on the ellipse boundary, on the ellipse, okay, then the W is 0, no? That's why we are choosing.
Yes, sir.
Not for any other thing. So it's only Robin condition where Robin boundary condition is 0. But that is the only thing you can do this kind of trick. So you consider the boundary itself, whatever form it is. Okay, this curve, closed curve into some constant, you take it, substitute into that, so you will get your that K. That K you can get it by substituting in this PD. Okay, so with that, I think this is what is done for elliptic. Similarly for triangle cross section. Okay, and that's it. That's what you have. Okay, so this is whatever you're seeing 8.11.4 is basically solving Laplace equation in using the separation of variables, which you might have done in your PD course. Okay, so don't worry about this style of doing. So that's how you do. Okay, so this is what we'll do. 1 or 2 hours we'll cover. So okay, we'll close the thing. Of course, there is one more thing is that I want to do. If you are interested, I will do. Flow path cylinder so far we have done now for the inviscid fluid. But for viscous fluids, you will have a drag. So that I think that also needs to be done. If you are still having energy, we will do it. Okay. So we'll do 2 to 3 hours. If we can finish this tomorrow, 1.5 hours, maybe next week 1 hour, I'll try. We'll have only that one. So we'll have a sphere or cylinder. You allow the uniform flow. Now you have a viscous fluid. Okay. Surrounding this cylinder or sphere, you have a sphere. Anyway, we have not done. We have done only for cylinder, right? That's why you see only circle in 2 dimensions.
Yes.
Similar thing you try to do here. There you have seen that your drag is 0, right? Drag is 0. Only lift was there because of when do you have a lift?
Only inviscid fluid, sir. Yep.
Yeah, inviscid fluid. When do you get the lift? Lift is coming for what? For what? So usually, if you have a cylinder, there is no lift, there is no drag, right? When did you
Sir,
get
if we rotate the cylinder and
only when you rotate that cylinder. So in that case only you got. So here in all the cases you will have a drag also here. Okay. Once you put the viscosity into your fluid, so you will have a drag also. That drag will come some number. So we will see that one as a final thing. Okay. With that your syllabus is over. Okay. So we need only 1 or 2 hours. We'll try to finish that one. So as you propose, I think I'll fix whatever I am teaching. I'll try to give after your midsem. Only just go through the notes. Only from the notes I give whatever I have done. Only I'll give as your questions. Okay. So perform well. Try to take interest and try to work out. Okay. So enjoy your holiday. I think I am spoiling your holiday.
no, sir, not like that. Actually, sir, some student didn't know there will be class, sir. Suddenly your message
Okay,
came.
that's okay. That's fine. That's fine. See, yesterday I have taken 1.5 hours, right? It's all right. Okay. So I will take tomorrow. Tomorrow is there. That's good enough. We have plenty of time. I thought
Yes, sir, yes, sir.
I was only rushing. Huh? Okay. I will see you tomorrow. Tomorrow at 11 to 12, 12:30. 11 to 12:30 is over. So all the
11 to 12:15, sir. Yes, sir. Approximate. Yes, sir. They had.
Joe is there. Joe is not. Huh? Joe may be. Okay. It's fine. Fine. Okay. We'll see maybe tomorrow. So you know, right? So you know overview of what we are going to do. Why you see in that circular cylinder, between the circular cylinders, if outer cylinder, if you rotate it, r and theta are depending both, right? So you have a plane. Your flow is only in the r theta plane, right? Cross section of the your cylinder, right? R theta. But r theta, once you have r theta, those unit vectors are depending on. So it changes, right? Those unit vectors r and theta actually changes its position. They are not fixed. You understand? Right?
Yes, sir.
So for that reason, you will have to change the term, that whatever that we have not done in your Carolinear coordinates, that is there unfortunately in your Navier-Stokes, that we will replace with something else, so that you don't need this theta cap, r cap. What is its changes? What is its derivatives with respect to r and theta? So those were just avoiding. Okay, so that way we are doing. But in order not to avoid completely, I have given you that video, no? So just see that one and try to derive. So I'm going to give you some kind of exercise. Please do it. Others are also. So whoever has done, so you just, some of you, Rishabh or Reddy or somebody, whoever is interested, just do it. Okay. Try to derive that third equation, the equation that I showed you, right? Where is that equation that I am showing you? Just now I showed, So where is that equation? I'll show you.
Okay, sir.
You have seen, no, that Carolinear code is the last equation. You derive it. Okay. I think I closed it. So, okay. So that last equation you derive it based on this, considering derivatives of theta cap and r cap also. Okay. Now derive that. So go back. So it's just try to go through the Carolinear coordinates lecture, and now this last inequality, right? U dot grad of u. That I want you to derive. Here, u in the place of u, you have f. So derive it so that it matches with that expression, whatever you have in that file, 2-page file. This file I'm going to give you as when you are writing the exam, so you can utilize it anytime. Okay.
Okay, sir.
Yeah. Okay. See you tomorrow.
Okay, sir. Thank you, sir.
Yeah.